Yeah, I have started a recording. Yeah, so I would like to hear your, your own mental definitions. What is probability? Okay, maybe I'll try to okay, anybody wants to answer? If not, I'll try giving hints. Okay, otherwise I'll try to make it, multiple choice type. Is it a number or is it a function?
It is a function.
Very good. Right? Yeah. So, yeah, probability of a particular event is a number, but that is what you obtain by applying this function to a point in the domain. Right? So it is cleaner and more general to think about, not probability of a specified event, but probability as an abstract object is a function. Okay, good, Krishnaveni. So once you commit that it is a function, there are two natural questions that come up, right? What is its domain? What is its codomain? So I'll ask the easier question first. What is the codomain?
0 to 1.
0 to
yeah, real numbers between 0 to 1, both included.
Yeah.
Okay, 0 is a valid probability, 1 is also a valid probability. So it is the closed interval between 0 and 1. Good. Domain?
Set of all events. Power set of the sample space.
Very good. The set of all events is a perfect answer. The power set of sample space is not always correct. Okay, it's correct most of the time, but it is not always correct. We'll see why. Okay, but since you use this, where is the highlighter? Yeah, since you use the word event space, I think it was Neha. Can you tell me what is event space? So that anyway, I don't need to go in this order. So.
Event space.
Wasn't that your answer that the domain is the event space?
Yeah.
No, so then what is event space? Yeah.
No, I told the set of all events.
Okay, fine. Then what is an event?
An event is a subset of the sample space.
Very good. Okay. So what is a sample space?
Sample space is the set of all possible outcomes of an experiment, random experiment.
Very good. So what is so? Yeah, I think this was the better order to do it. Okay. What is a random experiment?
Random experiment is an experiment that,
yeah, the only okay. So this random experiment is somehow usually any description of probability starts with this idea of a random experiment, but and then you say that okay, why is it called a random experiment as opposed to a deterministic experiment where every time you perform this experiment the answer is the same, whereas in a random experiment each time you perform the experiment the outcome can be different. Okay, so it needs to have one outcome. That's the only requirement here. But even this definition of random experiment, I personally don't like, right? Because you can ask what, whenever you think about an experiment, there is this idea that it should be repeatable. It should be, we should be able to do it as many times as you want. But that is not true of many things on which we assign a probability. Right? Like we ask, what is the probability that there is life outside of Earth? We are not doing any random experiment, right? Okay. But you still ask, what is the probability that there is life outside Earth? Okay. So in that sense, this definition of random experiment is tricky, but you will see that for the mathematics of it, actually, I was happy that among the 3 questions that I asked Neha, she took the maximum time to answer the question on what is the random experiment. It's because that's the one that is not really, very cleanly defined. And you'll see that you don't need, in none of the formal definitions of probability, this guy comes in, right? in none of the formal definitions of probability, this guy comes in, where you can really start by saying that the sample space is any set. Mathematically, nothing is lost. But if you are a physicist, if you are an engineer, if you are trying to model something which has inherently a randomness inside of it, then it matters. But for the mathematical formalism, you can start by saying that your sample space is any set. And set time assuming is a definition, well-defined object. Okay, I'm kind of not going into the complexities of defining the notion of set itself. The event, as Sneha rightly pointed out, is any subset of the sample space. And the event space is nothing but all the events that we want to consider. Okay. Now, here there is a caveat. When I say all the events that we want to consider, you may ask, then why not consider the power set of the sample space? Okay. So if your sample space had only finitely many points, then there is no harm in considering your event space to be the power set of sample space. So every subset then qualifies to be an event. But when your sample space is continuous, okay, if the sample space itself is a interval of numbers, or think about rotating some needle and see what is the angle at which it will finally settle. This is a very nice random experiment, right? And the angle can be anywhere between 0 and 2 pi in radians. Okay, so this is a continuum. In these cases, there is a mathematical difficulty associated with defining, or if you say that every subset of this continuous set is an event, then there is a mathematical difficulty which comes in later. Okay, that is that difficult at this point. There is, at the level of talking about events, there is no difficulty. But when you try to assign probability values to these subsets, you end up resulting, you end up in impossible situations, right? So those who are from the math background might already know that what I'm talking about is the risk with non-measurable sets. The probability is a type of measure, and you can assign probability only to a measure space, and the power set of the continuum is not a measurable space. Okay, there would be due to these famous constructions. I'm forgetting the names. Okay. Yeah, so due to slightly non-trivial technical difficulties, you won't be able to assign probabilities which obey the natural rules that probability should obey. This additivity, monotonicity, etc. You won't be able to do that. Okay, so that's why I said Sneha's answer that event space is a collection of events. Is the domain of probability is the event space. Okay, it is the collection of events that we are interested in. In this course we will limit to discrete random variables, and hence we will limit to discrete random variables, and hence there is no harm in taking the event space to be the entire power set. But if you are in another course, where continuous probability is dealt with, then you will not be able to take the power set of the sample space as event space. But then, since we cannot always take the power set of the sample space, we try to bring in some restrictions on choosing the event space. In particular, we want to choose it in a way that if two subsets are both defined to be events, then their union is also defined to be an event. Their intersection is also defined to be an event. And I think one of this we have to extend to countable unions also. Is it okay? My measure theory I have started forgetting. One of these requirements we have to extend not just to pair of events, but to any countable collection of events. I think one of this has to be true. If you have a countable collection of events, then their intersection or their union also is an event. Okay, but please check Wikipedia. I don't want to go back and check Wikipedia. Then the empty set has to be event. And then if a particular set is an event, its complement also has to be an event. Okay, so these restrictions essentially put demands on some closure properties on the event space. Okay, and if you think intuitively about probability, these are all very justifiable demands, right? Because you think, because these are natural questions that people can ask. You tell them probability of event 1 and probability of event 2. It's natural to ask, what is the probability that both of them will happen, or what is the probability that there are aliens and there are harmful aliens, right? So these are natural questions. Or things like, if you ask, if you say that this is the probability of an event, what is the probability of this not happening? And we all would say 1 minus the earlier probability, but then you would be kind of embarrassed if it turns out that the complement of this event is not an event. So in order to prevent such embarrassments, we put in these requirements to the event space. Again, for those who have done a course in measure theory, the requirements of event space is precisely the requirements of a measurable space. Okay, now, yeah. So now we have a definition of what is probability, right? So it is a function from the event space to the closed interval of real numbers, the closed interval 0, 1 of real numbers. Okay. Which again, it is not. Does any function from this domain to codomain qualify to be a probability function?
No, because we need the union of two disjoint events to be the sum and other stuff like that.
Correct. So we need the additivity property of disjoint events if E1 and E2 are disjoint events. Now, before getting there, let me draw your attention to the sentence we are using, right? We are saying events are disjoint. Okay, so because of our definition of event as a subset of the sample space, the word disjoint correctly fits in there. There is no confusion. But if you use the English meaning of the word event, as to something is happening, then maybe this union you will have to think of it as an or and so on. But yeah, so it's important that you understand it in both contexts, right? In a logical sense, it's an or. What is union becomes an or. What is intersection becomes an and so on. Yeah, but coming back to Abraham's point, this probability distribution needs to satisfy this additional axioms, right? I think there are 3 axioms. Probability of the empty set has to be 0. Probability of disjoint events. Again, I think you need countable additivity. Okay, so which means now I get the answer to the demand on the event space also. So what is the event space need to be closed under countable union? Because the extension of what Abraham said is, if you have a sequence of events E1, E2, E3, which are pairwise disjoint, then the probability of their union has to be sum of their probabilities. So there are immediate consequences for this. Like you can prove that I was trying to prove that the probability of the complement is 1 minus the probability using just the additivity. But for that, we need to put in an axiom saying probability of the entire sample space, which is also by definition a subset of the sample space, is 1. So I think that also goes in. Yeah, I should have revised this axioms of probability. Okay. Now, next question is, this is a complicated function to. By the way, again, for those who have done a course in math, this requirement essentially is telling you that the function is a mesh. It's just telling you that it's a measurable function. No, it's telling you that it is a measure, and this extra requirement that we put in the beginning, that it's a value between 0 and 1, makes it a normalized measure. Okay, but but the next point I want to highlight is that since the domain is this event space, it's slightly complicated to define, to assign actual values to this function. Okay, so most of the time we assign these probabilities in a two-step process. Okay, in a discrete sample space, right? If the sample space is only a countable set, if it's only a countable set, then we can assign probabilities to individual points in the sample space, right? Our aim is to assign probabilities to events, the subsets of sample space, but we start off by assigning probabilities to individual points in the sample space, and then you find the probability of any event, any subset, by an addition. So if the set is finite, the addition would be your normal addition. If it is an infinite set, then you may have to kind of do a limiting sum to find the probability. And this first step, this assigning probabilities to points in the sample space, is usually known as the probability mass function. Okay, so in the discrete case, you do this via the probability mass function PMF, but this cannot be done on the continuous case, right? Think about the needle experiment. If you start assigning probabilities to individual points, there are uncountably many points. So if you assign non-zero values to them, the total probability will be infinite. Okay, so this idea fails there, and there we have to work with what is usually known as the probability density function, PDF, if it is the continuous case. Okay, so continuous, we will work with PDF, and we won't work with the continuous case, but I'm saying, and this probability density function is a notion where in any interview, 99% of the people mistake it, because it's not a probability, it is a density. For example, its value can be, its value is still non-negative, but it can be much higher than 1. Okay, because you get probability then by integrating this probability density function over the event that you are considering, right? So in normal cases, normal integration would work, but in the most general event space, you may need a Lebesgue integration to actually do this integral, but it's not a concern in this course. But you should remember that this probability density function, the words probability and density should not be split. It is never a probability function. It is not even bounded at 1. It is a density. It is like, an object whose total weight is 1 kilogram can have intermediate points where the density is very high if this object is really skew spin, right? So that difference you have to keep in mind. Okay, so we will keep the continuous thing aside. Let's go back to the discrete distribution. So here, most of the time, the way we are going to assign probabilities is using probability mass functions, which are nothing but probability values assigned to singleton events which consist of only 1 point in the sample space. So there it is correct to think of it as a probability of an event, a singleton event is what it is. Now there are interesting questions as to what would you do if your probability, your experiment has both a continuum and a few discrete possibilities. There are such interesting questions which is usually dealt with in a course in probability theory. But one thing that we still have to consider is, suppose your sample space is discrete, but still an infinite set, like natural numbers. So can somebody think of a PMF which you can assign when the sample space is the set of natural numbers?
We just need a series that converges to 1.
Yeah, we just need a
which
series.
Is positive. Yeah.
Exactly. We
With
need a non-negative series, right? 0 is allowed, a non-negative series where the sum converges to 1. This automatically means that the individual values would be less than 1. Can you give one such example?
1 by 2 raised to n.
Yeah, 1 by 2 raised to n. Yeah, if you are assuming natural number starts from 1, 2, 3, etc. If it starts from 0, then you may need to half the whole thing. Right? So this is one way to do it. But then this is only one example. There are many other ways to do it. The general geometric distribution, if you remember, is some such thing. By the way, you could have assigned non-zero values like maybe 0 is with a probability half, 1 is with a probability half, PMF is 0 on every other values. That's also technically correct, but I am happy that you understood the spirit of the question, that we want non-zero probability values sitting on infinitely many points in the sample space, right? So this is still possible in the countable infinite case. So this is another major difference between a countable set and an uncountable set. In an uncountable set, you will not be able to assign non-zero values, positive values to uncountably many points and then hope that their integral will be finite. Okay, so that's about continuous and discrete distributions, and this how you usually define them in terms of PMF. Okay, now next term that I want all of you to be familiar with is a random variable. So what is a random variable?
So it's like a variable that we are assigning, which can assume some value.
Okay, so let me try to make it a multiple choice question. Is it a number, is it a variable, or is it a function? 3 choices, okay, A, B, C.
Sir, it is a function.
Okay. So good, Vishnu. It is a function. Again, I mean, it's not wrong. What Lalit said also, I'm not saying he's wrong, because, this notion of variable itself is, in a proper foundations of mathematical course, we wouldn't, it's not the variable in that sense. Okay. It is not a quantity, which is unknown now. Okay. It is not in that sense that, that meaning of variable does not fit in here. But as Vishnu said, it's best to think of random variable as a function. And yeah, now that begs 2 questions, right? What is the domain and what is the codomain? So here again, the easier question happens to be what is the domain? So what is the domain of a random variable?
Sir, it can be the sample space.
Exactly. So the domain of the random variable is the sample space. What is the codomain?
Sir, it will be a real line.
Yeah, it would be real numbers. Is it necessary that it has to be between 0 and 1?
Yes, sir. It may be 0 or 1. But most
Okay, but
likely
that
it
is
is
not true.
between-
That's not true, Vishnu. In fact, random variables can be negative, right? For example, the number of students who turn up to each lecture, that is a random variable. And the
Yes.
number can be anywhere between 0 and 15, if you think about this course, right? So there is no upper bound or lower bound. The codomain is the entire real line. Okay. So yeah, so you should not confuse between probability and a random variable. They differ in both the domain and the codomain. The domain of random variable is directly the sample space, whereas the domain of the probability measure is the event space. Similarly, the codomain in the probabilities case is the closed interval 0 to 1 within the real line. For a random variable, it is the entire real line. Okay. Now, again, this question has to, can any function from sample space to R is what I call the real line. Does any function from sample space to R, there is sample space, our typical notations are omega.
Sir, why R?
I'll actually come to that question. Yeah. So, okay, maybe since you asked, let me go to that question and then come back to this later. So in classical definitions of random variables are defined to be real valued functions on the sample space. Okay. But modern, more abstract treatments do not put this requirement. In fact, the codomain could be any measurable space. Okay. So for example, you can have complex valued random variables. You can have vector valued random variables. We treat them, for example, the point of a Brownian motion, if you think about it, point of the position of a point, right? You need not one real number, you need 3 real numbers. So I mean, there is nothing, the classical definitions are not wrong. You can think of it as 3 random variables, but there is some advantage that you get if you think of them as a 3-dimensional random vector instead. Okay, so these are vector valued random variables, or more commonly known as random vectors. There is a further extension. Instead of 3 dimensions, why can't you have infinite dimensions, right? Why can't you have an entire time series? Then you have random series or random processes, as it's mostly called, right? If you trace the evolution or the trajectory of a point, a dirt particle in air, if you trace its trajectory over 10 minutes, right? Then this can only be represented as a function, okay? A function with what? Whose domain is time and whose range is r cubed, right? So even such objects can be random variables, right? So yeah, so the answer to Abraham's question is that, yeah, there is no need for it to be a real line, okay? But then there is also this question, then why do we really, impose this function random variable on the sample space? Why don't we work directly with the sample space? Okay. So this reason is that we want to convert it, want a mapping to a codomain where algebra is possible. We want to add things, we want to multiply things, we want to negate things and so on. So the choice of the codomain is essentially a kind of set where there is a lot of algebraic structure. All the examples that I gave, real numbers is not the only place where you have algebraic structure. Complex numbers have as good a algebraic structure as real numbers. Vectors have an algebraic structure. So the difference between the domain and the codomain is that in the domain, like think about heads and tails. You find it difficult to add head and tail, right? Whereas if you convert it into 0 and 1, then you can even talk about what is the average value. Otherwise, how do you talk about average or expected value? So that's the thing. So the physical intuition or the original motivation for a random variable was as a measurement process. So measuring is this art of quantifying things. So the job of a random variable is to quantify your outcome of the experiment. Okay? So it is mapping from a sample space to a place where you generally associate measurements, which popularly happens to be real numbers. Okay. Abraham, did I actually answer the question
yes,
you
sir,
had
yes,
in mind? Yeah. Okay.
Excuse me, sir.
Yeah.
To add on to that point, I just want to know, like, since you also mentioned about adding different dimensions, so that for random variables in the codomain. So I was wondering, like, is there any specific reason to do that? Because anyway, they will serve the same purpose, right? Because they don't add any. So like real number has the same, like, algebraic, the kind of algebraic property it has. I mean, the things that we require for probability is kind of given as already real numbers. So if we add any other codomain, they will also serve the same thing. So why, like, I don't see any.
Excellent question. Excellent question. Okay, excellent question. And philosophically, this goes very deep into the philosophy of science itself. I think it was like what, Thomas Young or somebody, right, who said that right, what is it? Measuring something is the beginning of knowledge, right? Everything else is an opinion. So the reason for now, let us only talk about random variables where the codomain is real, okay, just to keep the discussion simple. The reason for doing that is exactly the reason why we are measuring things, right? Why we are measuring heights of people in centimeters, or why we are measuring the temperature of an object in degrees Celsius, or why we are measuring the intensity of a light in lumens. It's the same reason why we are trying to quantify a sample space or measure the outcomes using numbers. Okay. Once you get them into numbers, there is a large set of questions, meaningful questions that you can ask, right? Like you can ask, what is the average temperature over the day, right? If temperatures was just a feeling, you did not put real numbers to it, right? You could not answer this question as to what is the average temperature, or what is the maximum temperature, or what is the minimum temperature, right? So the reason to do it is exactly the same reason as to why we measure any physical quantity. Okay. In some sense, think about grades versus marks. Okay. If I give you a grade, then you really cannot ask the question, what is the average grade in the class? We kind of do a workaround. We do the silly thing of first giving a grade and then giving this grade point so that you convert the grade back to a number and then take the grade point average of the class. But that's not the grade average, right? The grades, if you have this SA, B, C, D, you cannot ask the question as to what is the class average or what is the maximum grade. In this case, you can still ask because there is an order among the grades. But yeah, or you want to say what is the stat, like if you want to say how the class is going together, is everybody on the same page or there is a big difference in the class, you can ask by checking what is the standard deviation in the marks, but not in the grades. Right? So that's the reason. That reason goes much deeper. It is relevant not only in probability theory, but it is relevant in all of science. Any other question? So Lalit, is it convincing?
Yes, sir. The example that you gave I got my answer.
Yes, but I was asking some question. Okay. So I should not forget this question. Does every function from sample space to the real line, does it qualify to be a random variable? Okay, again, here the answer is technical and it is no in general. Again, this I am only talking to those who have done a course in measure theory. It needs to be a measurable function. Why? Because if you take any interval on the real line, right, and then you want to ask what is the probability that the random variable's value is inside of this interval, which means you have to go to the pre-image under the random variable and find out the event, the subset of the sample space, which will map into this interval under this random variable. And that subset has to be an event for you to talk about its probability. And this, if you recall your definition of a measurable function, is exactly the definition of a measurable function. Okay, the pre-image of any measurable set has to be measurable. That's the demand. But since we will be limiting ourselves to the discrete sample space and the power set as your event space, this pullback condition is trivially satisfied because every subset is an event. Once you pull back the thing, whatever set you get is an event. So this does not apply. So if you're only talking about discrete distributions, then any function from any measurement, any function from the sample space to the real line qualifies as a random variable. Okay. Examples are assigning heads to 1, tails to 0, or assigning measuring the voltage across a resistor in a circuit and expressing it in, let's say, volts so that you get a real number, and so on. Right? So this is a random. And as in order to answer Lalat's question, I already hinted about this expectation, right? So what is the expectation of a discrete random variable? It's a weighted average, right? So if X is a discrete random variable, then expectation of X is, you look at all the possible values that this X can take. And why can I do a summation? How do I know that this range is going to be discrete? Because if the range is discrete, then the summation makes sense, right? That's because we are talking about discrete random variables. So the sample space is discrete, which means any function from the codomain is the entire real line. Codomain is a continuum, okay? But the range which sits inside the codomain is going to be a discrete set. So I cannot do sigma x element of R, but I can do sigma x element of range of X. And what do I multiply? I multiply X with the PM of evaluated at X. Okay, let me just call it P of X. So this is nothing but the weighted average. You weight each value of the random variable with the probability of that random variable. P of x is nothing but you, okay, maybe I skipped one step. I should have asked this question. Is it necessary that a random variable is an injective function?
No.
So let us say I toss a coin. Sorry, better example. Okay, let us say I throw a die and I say that for every even number, my random variable, the function, the random variable would be 0, and for every odd, it will be 1. Okay, so the measurement is nothing but the parity. So it's not an injective function, but is it still a random variable?
Yes.
Yeah, so it is still a random variable. So you don't need injectivity. So I want you to pay attention on what then P of x is. Okay, so in the like, let's say your x is this the random variable. So this is your R, but you have only discretely many points here. So it will only be mapped to discretely many points. Say this is your little x that you are speaking about, but it is still possible that 3 points in the sample space got mapped to x. Then this P of x is the probability of this event, which consists of these 3 sets. Okay, so even though we are talking about 1 point in the codomain, the pre-image, because it's not necessarily an injective function, the pre-image can be a larger set, and hence you really talk about the probability of this 3-sized event here. Okay, yeah, so that caveat, I think it's already 10 o'clock. I should not delay it further. So yeah, this expectation is another thing that you need to know. And we will use a lot of time this idea that expectation is linear. If x and y are 2 random variables, then expectation of x plus y is nothing but ex plus ey. That we will use a lot of. Okay. Yeah, unfortunately, I don't have time to go into the history. It is a nice history, and there was a lot of ridicule to probability early on, because people thought it's only about gambling, and gambling was not considered a very prestigious activity and so on. But yeah, it's a very interesting read, especially the work by Fermat and Pascal on how they had to stop a game in between. It was a game which involved money, and then when they went back home, and then using letters, they argued as to what is the fair way of splitting the prize money based on the chances of quantified chances of who will win and so on. Kolmogorov is the one who really